Hey everybody, we're here doing the midterm exam practice problems. And of course this is a Welty solution set here, so I'll claim it with my name there. Alright, this is going to be a while, but you can obviously pause, fast forward, and scan to get all the right answers here and check your work. Alright, away we go. So first one, number one, this is all in motion. So the sprinter runs 100 meters, 15 seconds. What is her average velocity? So we're looking at our average velocity is distance over time. And if I take 100 meters here over 15 seconds, we're going to get, calculator in hand everybody, and that is going to be 6.67 meters per second. Got it. All right, number two, bicycle accelerates at 2 meters per second squared for 2.5 seconds. How far does it travel? So if we look here, this is for constant velocity with distance, but we're accelerating here, so we have to look at accelerated motion for a certain amount of time will tell us the distance we travel. So that's our relationship we're going to use there. Distance during acceleration is 1/2 AT squared. So my acceleration rate is 2 meters per second squared. Right, my velocity increases by 2 every second. And we're going to do that for 2.5 seconds. Remember, it's time squared. So if I do 2.5 squared times 2 times 0.5, I get 6.25 meters. Got it. All right, number three. While driving your car at 27 meters per second, you hit the brakes. So you're going to decelerate, a negative acceleration of 3 meters per second each second. How long in terms of time does it take you to stop? So usually when I see acceleration, I think of the acceleration equation here. Acceleration is change in velocity over time. And hey, if my acceleration is -3 and my velocity is going to 0 from 27, right, it's final velocity minus initial. How long will that take, right? So these negative signs are going to cancel out. So I'm going to have -3 equals, I just said they cancel out. Well, see, get with the program. So I'm going to have 3 equals 27 over t. So what do I divide 27 by to get 3? And that is obviously 9 seconds. Got it. All right, upward and onwards, folks. Oh, we're on to graphs. Here we go. I surprised myself. All right, number 4 and 5 are all about graphs. Here we're looking at position time graphs, and we want to recall that the slope, I'll do it in red, the slope of a position time graph tells you about velocity, right? That's the thing we need to know. And if you forgot that, we could say, oh, if I look at slope, hey, rise is in position divided by run for time, and position divided by time, hey, that's what velocity is. All right, so if we look at the slopes here, here we have a constant positive slope. So this is a constant positive acceleration. Oh, I'm sticking with red. All right, no worries. So let's say constant velocity. All right, that's positive, right? All right, if I look at this one here, this is a constant negative slope. So here I have a constant negative velocity. I'm just going to write it right on the graph, everybody. Ooh, negative velocity. All right, I should put the positive in on the other one, right? Positive, got it. All right, here when I look at this slope, well, this slope is changing. It's not constant, right? This slope keeps getting steeper and steeper and steeper and steeper. So if my slope is increasing, that means my velocity is increasing for this one, right? So that would mean a positive acceleration, right? Since my slope is increasing, that tells me that my velocity is increasing as well. And that's what acceleration is. All right, cool. Number 5. Describe the motion of these velocity time graphs. Now the slope is going to be something different. I'm going to go to a different, I'm going back to my, we'll go to green. All right. So here, slope, if I do rise over run here, it's going to be acceleration for these graphs, right? And again, if you forget that, when I go rise in velocity divided by the run for time, a velocity over time is acceleration. All right, so if I look at the slope here, velocity time, this is a constant slope of 0, right? 0 slope. So if it's 0 slope and slope is acceleration, so that means I have 0 acceleration here. All right, so we're really at rest. Well, I'm sorry. Ooh, welting stop. Right, this means we're at a constant velocity here, right? If we're not accelerating, that means our velocity is constant. And you can see on the y-axis there, we have a value for velocity. All right, cool. Second one here. Here I have a positive constant slope, so I must say that have a positive constant acceleration, because slope tells me about acceleration. Here I have a constant negative slope, so there I have a constant negative acceleration, right? We're going to be slowing down from some higher velocity to 0 velocity. Got it. All right. We're still going, everybody. Oop, not at that rate. All right, so that's our motion stuff. And now, oops, sorry about that. Motion in 2 dimensions, right? So now we're looking at projectiles. And for this one, we start off with we've got our cannon. We're shooting our cannon. And it hits the ground. You're welcome for the sound effects. We're going back to blue. So it says, how much time does it take for the cannonball to hit the ground? So keep in mind, as this is falling, this cannonball is really in free fall, just as if I dropped it, right? So we know in free fall, things accelerate at negative 9.8 meters per second squared. Okay, so the question is, how long does it take to fall 10 meters when I accelerate at this rate? So this is just like the one we did in the motion prob, like the distance I fall when I accelerate at a certain rate for a certain amount of time. And that is, let's see, so we fall 10 meters, right? And we're going to accelerate at about 10 really, but we'll keep it 9.8. All right, so how long will it take to hit the ground? So, all right, we got to do a few math steps here, right? 1/2 times 9.8 is 4.9. So I'll get that over here. Still times t squared, right? And that equals our 10. We want to get t squared all by itself, so we can divide both sides by 4.9. Got it. So 10 divided by 4.9, this cancels out. So 10 divided by 4.9, my solar power calculator just went off. And it's a little dark in here, I get it. 10 divided by 4.9 is 2.04. All right, so this then says that t squared is 2.04. Well, then I got to take the square root of both sides to find my t. So the time to hit the ground is square root of 2.04. I've got 1.43 seconds. Got it. All right. What's the horizontal range? How far will the ball travel this way? There's my range. We'll do it in green, I guess. You know, how far out are we going to go if we're traveling at 30 meters per second for 1.43 seconds? So keep in mind, the horizontal velocity of a projectile is constant, assuming no air resistance. Oh, that's number 3, right? Horizontal velocity is constant. We can go out of order. It's all good, everybody. Right? So that is what's true about the horizontal velocity, is constant. Right? It doesn't change. So for this problem, if it's 30 meters per second, it's always 30 meters per second the whole way. All right, so back to this. So that means our horizontal velocity is distance over time. And if our velocity is 30, how far do we travel in distance in 1.43 seconds? So if I just cross multiply these two together, 30 times 1.43, I'm going to get a range or distance of, okay, it's about 43. So 40, that's a bad 4. I'll do better. 42.85 meters is what I got. All right, cool. We answered some of those other questions. We did number 3 already, right? Horizontal velocity is constant. Vertical velocity, well, hey, that's going to change, right? Because as this falls, it's in free fall, accelerating at negative 9.8 meters per second. So that is what we can put in here for this one. Yeah, vertical velocity changes, right? Changes due to gravity by negative 9.8 meters per second each second. All right, number 5, we actually kind of addressed it before. Number 5 says, hey, if you dropped another cannonball at the same time as the original cannonball was fired horizontally, which one would hit the ground first? So we kind of talked about that, or I referenced it up here, because if I just drop a cannonball at the same time I fire this one, they are going to hit the ground at the same time, right? Reason why is their vertical motions are the same. They're both in free fall. So just because this has horizontal velocity, that's just going to affect its motion horizontally and give it some range. But they will both fall at the same rate vertically and hence hit the ground at the same time. Okay, so we can write that down here too. Let me scroll down again. Yeah, if another cannonball, right, same time. Both hit the ground at the same time. At the same time, because, give us a reason, because both are in free fall. Right, the vertical motion is the same, and that's what determines the time. Okay, upward and onward to forces here, right? Okay, we got a little crooked there, everybody. Sorry about that. All right, so the key to this page here is looking at force diagrams and identifying the forces that act on these objects. So for the first one says, hey, we have a 1,500 kilogram elevator car traveling downward at a constant velocity, right? So you get in the elevator car, going down, 4th floor to 1st floor, whatever it is. And it says, draw a force diagram representing the two forces acting on the elevator car, right? So clearly we can look at, and we see the cable here, right? So we know the cable is going to pull our car upwards, which is a good thing. And then we also have a force pulling the cable car down, which is the force of gravity. So let's sketch those two forces in. So here we've got the force of tension due to the cable in the elevator, and then we also have the force of gravity pulling down. So those are our two forces here, okay? And it says for B, calculate the force of gravity of the elevator car, right? So force of gravity, that's just the mass of the car times the acceleration due to gravity, or 9.8. So we can do that right here. The force of gravity of the elevator is its mass times g, right? Which is, what, 1,500 kilograms times 9.8. Got it. If I do that out, 1,500 times 9.8. I'm calculating it live, everybody. Ooh, 14,700 newtons. I almost said joules. That would be energy. All right, so 14,700 newtons is the force of gravity on the car. Now it says, hey, since the elevator car is in equilibrium. So what is that, right? So equilibrium, it already said that it's traveling at a constant velocity here. So that's really what we mean by equilibrium. That there's no acceleration rate of the car. It's not accelerating downward. It's not accelerating upward. These two forces then must be in balance. So I should actually go back and make sure I draw the force of gravity the same length as the force of tension vector here, okay? So yeah, that's what constant velocity means. It means our net force is going to be equal to 0. So if I do that right here, a net force, right, that's the force of tension upwards minus the force of gravity down. And since any net force is mass times acceleration, So since we're not accelerating, it says constant velocity, right? Which means our acceleration is going to be 0. Okay, so that means this whole thing's going to be equal to 0. And the force of tension and gravity will end up being equal, right? And so that's our big deal, that these are equal and balancing each other, so we travel downwards at a constant velocity. Got it. All right, let's pull things horizontally here. That was a vertical problem. So let's look at pulling this box across the floor. And yeah, there we go. All right, so it says a 5 kilogram box right here, it's 5 kilos, is pulled to the right across the floor. We're pulling at 30 newtons, by the way. And it says the force of gravity is pulling down on the box at 49 newtons. And there's another force, the normal force on the box, pushing upwards on the box at 49 newtons. Now, normal force, keep in mind, the normal force, this is just the ground pushing up on the box, right? So this is due to the ground pushing up. That's all the normal force is. Right? The box pushes down on the ground, and in turn, the ground pushes back up. Kind of like it is a Newton's third law thing, actually, right? Action, reaction. Okay. And we have another force here, if you notice, kinetic friction, right? So as we're pulling the box across the floor, we have to go against kinetic friction as this box is sliding across the floor, right? So it says if the coefficient of kinetic friction, mu k, is 0.3, what's the force of kinetic friction? Well, if you scroll back up, there are some other equations up there. By definition, the force of friction, or kinetic friction, can be, it's the coefficient of friction times the normal force, right? If we think back to our definition of friction, friction depends on the surfaces in contact and how hard they're pushing on each other, right? So if you're rubbing your hands together, it's the surfaces of your hands and then how hard you push your hands on each other will determine how much friction and hence how much your hands warm up, right? So it's the same idea here. So if we know, yeah, we can calculate force of friction here. So we have all these numbers, right? So mu is 0.30. The normal force is given to us, it's 49 newtons. So if I just multiply those out, 0.3 times 49, and that tells us the force of friction is 14.7 newtons. Got it. Oh, and I'll label it right over here. I'll do it. So now it's 14.7 newtons to the left. Okay? B says, hey, if the applied force is 30, yep, what is the horizontal acceleration, right? So we can look and say, hey, the box is going to move horizontally, right? And there's two forces acting on it. As I pull it this way with 30 newtons, friction's pulling back the other way with 14.7. So I'm looking at the net force now on the box is made up of these two forces. It's the applied force to the right minus friction that I'm pulling against, okay? And that will cause the box, the mass of the box to accelerate. So if applied force is 30, force of kinetic friction is 14.7, right? And the mass of my box is 5 kilos. What's the acceleration rate, right? So what is the net force? 30 minus 14.7 is, calculating as we go, 15.3 newtons. So that's our net force. Our box has a mass of 5 kilograms. So what's the acceleration rate? Yeah, I just need to divide both sides by 5. And I will get an acceleration rate of, where's my drum roll, everybody? Oh, I just had it on the calculator too. 15.3 divided by 5 is 3.06 meters per second squared. Got it. All right, last one for this says, hey, why does it require more force to get the box moving from rest compared to keeping it moving? So you've got to imagine if I was pushing or pulling on this box, it's going to take more force to get it to move. And then once I get it moving, it's just going to move across the floor more easily. So that has to do with the difference between static and kinetic friction, right? Static is the friction of rest. Right? If you're static on the couch, you're just sitting on the couch. Versus kinetic, hey, you're moving, right? And this moving friction is less than the static friction. So if you go back and check over notes here, the force of static friction is greater than the force of kinetic friction. Hence, I need to pull harder to get things moving from rest and overcome static friction than I do for kinetic friction once it's moving. All right, we're onward to conservation laws. Here we go. Conservation laws. All right, we're starting off with conservation of energy. All right, we've got this ball here. It's already rolling, and then it's going to roll down the hill whoop, to point Y, and it's going to roll back up the hill to point Z, which is a little bit lower. We're assuming no friction here, so it's just going to keep on moving as we go. So it says, all right, hey, what's its potential energy when it's 10 meters above ground level here and rolling? All right, let's do it. So PE here, as we see, right, it's due to gravity, so it's M times G times H. So I can take, what is it, 20 kilogram ball? 20 kilos times 9.8 times 10. And I'm going to get, it's going to be like 2,000 or so, right? 20 times 9.8 times 10. 1960. I was not born yet. But 1960 joules, right? All right, so that's how much PE we have up here. I'm going to write it up there. Why not, Welty? 1960 joules. Got it. All right. And obviously, those 1960 joules, we're going to lose PE as we roll down here and gain kinetic energy, right? And then as we roll back up, we're going to increase some PE and lose some kinetic energy as we pass by point Z. So it says, at point Z, we have 960 joules of KE. All right, fine. What is the velocity of the ball at that moment? So I'm going to write it right on there that the KE here is 960 joules. Got it. All right, so kinetic energy is 1/2 mv squared. Depends on your motion. Well, it really depends on your motion because it's squared. So 960 joules of KE times, and that's 1/2. The mass of the ball is 20 kilos again. It's like some medicine ball kind of deal. Times V squared. All right, so I have to do some math steps here. 1/2 times 20 is 10. And then I'm going to divide both sides by 10 here. So I'll write it out, everybody. Don't panic. 960 equals, so 1/2 times 20 is 10. All right, times V squared. Divide both sides by 10. Got it? All right, so it's going to be 96. Did the math in my head. So 96 equals V squared, and I got to square root this stuff to get V. So where's my drum roll? Square root of 96 is, weird, basically 9.8 meters per second. That's funky, huh? Coincidentally, the same number as acceleration due to gravity, right? Totally coincidental. So its velocity, it's going to be moving here at 9.8 meters per second. Has nothing to do with gravity, just by coincidence. That happens, everybody. You just make these numbers up. All right. At point Z, here we go. So, 960 joules of KE here, I get it. If the total energy there is 2,000, how much PE do I have there at point Y, right? So, all right. So let's do a little KE, PE, total energy thing, right? T is total energy, right? TE. So it says we have 2,000 joules total, right? And keep in mind, if I add these together, kinetic plus potential, I'm going to get the total energy, right? We're assuming no friction. It didn't say it before, but I'm saying it now. So we're assuming no friction. So 960 plus how many joules is 2,000? All right, I'm on it. So total energy here is going to be the sum of potential there and kinetic. And if the total's got to be 2,000, and how much PE do I have? If I have 960 joules of KE, So I just subtract, and I'm going to have how many joules of PE? 2,000 minus 960. Oh, I got 1040. That's a nice number, 1040. 1040 joules of potential energy there. Got it. I'm going to write it in. Ta-da. All right, what else we got to do, everybody? So scrolling down. Oh, all right. At what point is the speed of the car the greatest? So when is it going the fastest? Roll in. That's going to be point Y, everybody, right? Because here at ground level, my potential energy is going to be 0. So here at Y, we're going to have 0 PE, right? Which means our total energy is going to be KE, which is that 2,000 joules. Yeah, that's handy, right? All right, so yeah, if I say that down there, yeah, point Y, oh, Welty. Sorry, I'm shifting everything all over the place. Oh, that's craziness. Sorry. Got it. Oh, that's even worse. Is that better? Did I make it better? Is that better or worse? That's better. All right. Sorry about that. These things just happen. So, yeah, so at point Y, right? Because you have the most kinetic energy there. Right? In fact, all your total energy is the form of kinetic. All right, number 5 says, how does the concept of work relate to raising the ball to point W? That should say point X. That's a little typo, guys, right? Because we're talking about X is right here. Got it. All right, sorry. So let's fix that typo there. This should say point X. My bad. Point X. All right, yeah, so how does work relate to raising it to point X? So remember, work, how I do work is a force applied for a distance. But what work does is it changes the energy of an object. So if we're raising it to a height, work is going to increase the potential energy of the ball, right? So if I look back up here again, somebody, at some point the ball was on the ground here, and we had to do work to lift it up to point X. So we had to apply a force equal to the weight of the ball, the force of gravity, times the height, and that increased the ball's potential energy. Got it. All right, the other question then says, how does power relate to that? Let's see. Yeah, so how does power relate to raising the ball to point X? Well, power, again, is just how fast I do work, right? It's the rate at which I do work. So it's all going to be depending on how quickly I do that work. So the power, this is really going to depends on how fast, right? How quickly I do the work, right? So if I lift the ball very quickly in a short amount of time, I'm super powerful. If it takes me a longer time to lift the ball to point X, then I would be less powerful. Okay, but it's all about time. All right, let's talk about momentum. Last page. All right, last page. We made it. This video is already 28 minutes. It is what it is, folks. You're not going to watch the whole thing for 20 minutes straight, are you? That's okay. I'm flattered if you do. Sorry, it's something on my glasses. All right, we're going to keep going. Home stretch. Actually, we're around in third, yeah, right? We're headed home. All right, conservation of momentum. We've got a red train car. I know you can't see it as red, but it is red, trust me. It's moving to the right at 8 meters per second, and there's another car here at rest, same mass, and it's going to collide with the green one, and then they're going to move off together as one car. So we actually want to see, how fast are they going to move together when they couple, right? That's what train cars do, they couple. And also, what type of collision is that? You may know already. So number 1, what is the momentum of the red car before the collision? So momentum of the red car, I should do it in red. I have that capability, everybody. I can step up my game. Momentum of the red car is going to be its mass times velocity. So it's 30,000 kilograms. And it's going 8 meters per second. that's going to be like 240,000, right? I did the math in my head. Let's do it. 30,000 times 8. That's right. 240,000 units of momentum, kilogram meters per second. Got it. Pardon me. All right, what's the momentum of the green car before the collision? Hey, it's not moving, and momentum depends on motion, so it is 0. All right, what's the total momentum of the system before, and after the collision? That's all in one question, Welty. So hey, the moment. Oh, careful, everybody. The momentum before, right? So momentum before, it's just the sum of the momentum of both cars, right? So I've got to take 240,000 plus 0, and that'll give me the momentum before. So I can write that as 240,000 then, right? Units of momentum, or kilogram meters per second. And remember, we say momentum's conserved in these collisions. Conserved is a fancy word for the same or equal. So this means that the momentum before has to equal the momentum after. So momentum after is also going to be 240,000 units of momentum, kilogram meters per second. All right, so now we're saying what's the velocity of the cars together after? So again, remember the momentum after is 240,000. And that's going now to be equal to the total mass. We really have one big car moving now, right? And that one big car has a mass of, it's a combined mass, right? So this would be 60,000 kilograms. Oh, it says it right there. 60,000 kilos. So how fast is 60,000 kilograms moving when it has that much momentum? So I gotta divide both sides by 60,000. That'll cancel out. Ooh, I really want to do the math in my head. I think it's 400? Oh, we're going to find out. So 240,000 divided by 60,000. Oh, it's 4. Welty. Got it. 4 meters per second. Oh, but that makes sense, right? Because you guys said in our momentum conference, actually, that, hey, if this car here, if I have this mass moving at this speed and now I double the mass, boy, if I double the mass, it's going to move at half the speed to keep the momentum the same number and to keep it conserved, right? 4 meters per second. Perfect. Right? Oh, what type of collision is this? Inelastic, because they stick together, but you knew that already. All right, let's see. There are a few more questions here about these cars. Oh, I'm supposed to circle it? Oh, Welty, that's craziness. You can circle it, no worries. All right, number 6, last question. Suppose the red car, it crashes into a haystack and comes to rest, or suppose it crashes into a brick wall and comes to rest. So our brick wall haystack example, right? For the haystack collision compared to the brick wall, describe what's the same for both collisions and what is different. All right, here's the deal, right? So they're both going to change their momentum by the same amount. All right? So this is going to be the same for both. Otherwise, both are stopping the car. Okay? Impulse equals the change in momentum. They're both, the haystack applies an impulse to the car, the brick wall applies an impulse to the car. They both change the car's momentum by the same amount. So these impulses are also the same. And you're like, but Welty, there's something different though. I know the haystack is better. Well, that's true, right? If we don't want the car to be destroyed, we want to make sure the time is super long, and we want to maximize the time and increase it, right? So this time here is going to increase for the haystack, right? It's going to be super small for the brick wall. It's going to be tiny, right? Which we don't want, right? Because if it's a short time for the brick wall, the force it's going to feel is going to be super big for the brick wall, right? And will do damage to that train car. But if the time is long, that collision lasts a long time, that force will be super small, right, for the haystack, and the car will be okay. All right, so again, hey, for these collisions, whatever they're colliding into at the same from the same speed, both of these objects, haystack, brick wall, are going to change the momentum to 0 to stop it. That's going to require the same impulse to do that for both, because impulse equals the change in momentum. But the impulse, how we apply the impulse, can vary. So haystack takes a long time to stop the car, and hence the force will be tiny. The brick wall stops the car in a very short time, tiny time, and hence the force will be a lot bigger. All right, that is all I got for the midterm practice probs. Have a good effort in preparing. TY.